All right, let's try Norman Nice's problem 829. Here's the actual problem over here. It's got a 0 on it. And what I did is I just threw out the 0. What happened to the 0? I just left it off. And so what our job here is to find K for closed loop poles that give a damping ratio of 0.55 damping ratio. And does this look like it has a justification? Does it have a second order approximation? Is it good for a second order approximation? So this is kind of, I'm going to leave this to you guys to do, but what I want to do is show you quickly. Let's draw a couple root locus, just sketch some out. 1, 2, 3, 4, 5, 6, 7, 9, 10. 1, 2, 4, 5, 6, 7, 8, 9, 10. So here's this is the, it's good. I can do this one too. If we don't know by now, the root loci are symmetric. So when we're doing root loci, what we know is they start at the open loop poles. S equals 0. S equals minus 10. And S equals minus 6. And so we need to put the open loop poles and zeros in. There's no finite poles, so we have infinite poles. And we're going to look at the real axis segments. We're going to look at the real axis segments. So we start to the left, and we start at minus infinity and work our way back to the left of each odd number pole and 0. 1, 2, 3. Well, that goes on forever because there's no more out there, so I'm just going to put a line out there. So then we want to find out, like, how many asymptotes are there? Asymptotes. There's a number of poles minus the number of zeros. There's 3 infinite asymptotes. There's a formula for this, and you can work it out, but we're just going to divide it. It's plus or minus 60 degrees. We divide the S-plane into 3 equal pieces of the pi, and it's minus 180. 180 and 60. So this is one of the infinite asymptotes here. The other 2 infinite asymptotes, we have to find out where that asymptote intercept point is. It's the sum of the poles minus the sum of the zeros over the number of poles minus the number of zeros. These are finite poles. So that's going to be minus 10 minus 6 minus 0 divided by 3, 16 over 3, 5 1/3. Here's 5 1/3. So here's sigma A right here. All right, so one of the things is we know this 60 degrees. I could get a protractor out, and I'm just going to estimate what 60 degree asymptotes are. I know 60 degrees, something like that. This is an estimate. Go use MATLAB to do that. You can easily just use the rlocus command. Rlocus GA. Maybe we have to do GA is equal to transfer function where the numerator is 1 and the denominator is s squared plus 16s plus 60 and 0. Maybe we have to do that. You can try that out. Okay, so the other thing is it says that says 0.55 is what you want. So for 0.55, theta, cosine theta equals zeta. That means theta equals the arc cosine of zeta. Then I use zeta equals 0.5. I use zeta equals 0. This is 0.55. Oh, sure, do it exactly if you want to, but we're doing a hand sketch here. This is like an exam, so this is 60 degrees. And again, I know what 60 degrees looks like more or less, so I'm just going to estimate 60 degrees here. So that's my zeta equals 0.5, theta equals 60 degrees. Right, so here we go. So now I kind of have to figure out where my breakaway points are. And there's a bunch of ways of doing the breakaway points. That probably the best way to do it is to just go ahead and say that KGH equals -1. That means K is equal to -1 over GH, which in this case is -1 times S plus 6 times S plus 10. And all you do is you plug in S. You say S equals 0. Okay, well, when S equals 0, then I can tell you that K also equals 0. And I can also tell you that when S equals -6, K also equals -6. And you just plug these in, and you just plug in numbers, and eventually you get to some point. I think this is about -2.47, something like that. But basically, you kind of, after you've done a few of these things, you kind of get some idea that this breakaway point, if they're exactly symmetrical, that it happens in the middle. And anyway, we're just doing a sketch, and this is an exam, so don't get too caught up in it all. So here's my root locus. Perfectly good root locus. And now it says find out what the gain is. So we can say, well, if this is what my damping ratio has to be, this box is where my gain should be. That's my desired pole locations. And if I want my desired pole locations, what I want to do, if I want to find out what K is, Kp is equal to K, here, let's start here. KGH equals -1, K equals 1 over the magnitude of GH. I'm going to use the magnitude criteria, and that means that it's going to be S plus 0, the magnitude of S plus 0, magnitude of S plus 6, magnitude of S plus 10, all over 1. So what are the magnitudes of those things? So we could go through a bunch of geometry to figure that stuff out, but I'll tell you what, let's just do this. Let's just do this. That looks like about 4 to me. And then, let's see, so that's, I have to write, let me draw the vectors. So that is S plus 0, I called it 4. Let me draw this vector here. This is a S plus 6. How big is it? I'm going to call it 5. And then here is the vector S plus 10. And I'm going to see how long that is. 9. Let me call it 9. It's a little under 9. Let's call it 8.5. I'm going to call it 9. I did the numbers for 9, so I'm just going to call it 9. Close enough for government work. So this is 4, 5, 9. If I multiply those all together, 4, 5, and 9, it gives me a gain of 5 times 4 times 9. I have to get my calculator out. 5 times 180. And so you can go check exactly where this is. So once you've done your rlocus command on here, you can also check, you know, to see where your damping ratio is by using the rloc find command. GA, you can try that one out. But basically, this tells us now what our closed loop control system looks like. K, P, and then a lot of times he just calls this G. For problem 28, 8.29, we've got a closed loop control system that looks something like this. We can look at what the closed loop transfer function is. The closed loop transfer function says that that's going to be Kp over numerator of G times the denominator of H divided by the denominator of G, S plus 6, S plus 10 times the denominator of H, plus the numerator of G times the numerator of H is that. And so I'll leave this for you to now multiply these out. You can also use the TS is equal to feedback command, feedback GA, comma, GA times 180, comma, it's got a unity feedback, and that'll give you the feedback, and then you can just do step TS and check all those things. So I show you this stuff because it says, you say, oh, okay, here's how my root locus goes. One of the things is when you have extra poles, when you just have two poles, you get infinite asymptotes that are vertical. When you have a bunch of any other poles there tend to warp the root locus so that it does go into the bad side of the plane, right? So now let's do the problem as is quickly here. Just do the problem as is quickly. Again, I'm just going to sketch. If I want it all to be accurate, I'm going to go and do a little bit of MATLAB stuff. If this is an exam, I'm not going to much. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to put 2 more on there for my own reasons, I guess. So now we've got a little bit different problem, right? We're going to start at the open loop poles. 5, s equals 0, s equals minus 6, and s equals minus 10. But now we have a closed loop 0 at s equals minus 2. A closed loop 0. So we're going to go, again, we're going to do the real axis segments. 1. Okay, that's the real axis segments. We're going to do the number of asymptotes, number of poles, minus the number of zeros, which is equal number of finite poles minus finite zeros, which is 2. And we've done this enough to know that these are at plus or minus 90 degrees. We want to find out what the asymptote intercept point is so we can draw the asymptotes. And the asymptote intercept point ends up being asymptote intercept point is the sum of the poles minus 10 minus 6 minus 0, 6, 0, minus 2 all over the number of poles minus the number of zeros. So that's going to be 16, 14 over 2, or 7. So my asymptote intercept points in this case are going to be minus 7. And so we, again, here's our asymptotes, here's our infinite asymptotes. And now we have a little bit different. Again, it's a little harder here because we do have these breakaway points that we have to deal with. Where are the breakaway points? It turns out this is where I did get into some trouble. Nobody's really telling you the easiest way to do this. If you have to do it, I mean, there's a lot of tools that'll do this for you, but some of the formulas don't work as well. Everything's not quite as good. It turns out this is like it's almost close to 8. And the easiest way to do that again is just to draw the number, to take S. So I know that Kp is equal to 1 over GH, which is equal to minus 1 times S plus 0, S plus 6, S plus 10 over S plus 2. And I can just run, it's got to be somewhere in from S equals minus 10 to S equals minus 5. And all I do is I plug in S. I can do this on the computer, and it turns out it's just real close to minus 8. But again, the asymptotes, it happens somewhere in between here. So, and then this thing, root locus, goes up and meets up with the asymptotes. So there's your root locus. And again, I'm going to try and draw my 60 degree mark here. See how accurately I can draw 60 degrees again. So this is zeta equals 0.5, theta equals 60 degrees. And so this tells me that these are my desired root locations. There's one down here too. Those are my desired root locations, right? And so if that's my desired root locations, I might be off by a little bit. Now I need to know if those are my good desired root locations according to my overshoot specification, then maybe what I want to do now is look at k equals 1 over gh. I want to use the magnitude criteria, which means that's going to be s plus 0, magnitude of s plus 0, magnitude of s plus 6, magnitude of s plus 10, all over the magnitude of s plus 2. And then all I have to do now is say, what are those vectors and how big are they? So here's s plus 10. Here is s plus 6. Here is s plus 0. And now I've got this next one, s plus 2. And so how long are they? You know, you can pretty much estimate these things pretty easily. But, you know, I'm going to at least, if I didn't do it this way, I'd at least get out a scrap of paper and I'd measure them with us against this scrap of paper. But I happen to have a compass around here, so I'll use that. So s plus 0, s plus 0. Oh, my compass is falling apart, sorry. Not very good. S plus 0, length of that. Okay, I'm going to call that 12. I called it 12 last time. That's why I put 2 extras here. It's a little bit more than 12, but, you know, I can refine the gain. And so here's s plus 2. How big is s plus 2? I'm going to call that, last time I got that to be 11. I'm still just going to do 11. If I fudged this square just a little bit, it'd be all right. But you get the idea. So, and then here's s plus 7. It's about 10. I'm sorry, s plus 6 is about 10. And then here's s plus 10 is also about 10. So let's just call them that way. So this is about 120 kp. 120. I'm going to round everything, right? That's close enough. And you can go find exactly what the answer is there. And then what your job is to say T of S is equal to numerator of G times the denominator of H. Numerator of G times the denominator of H divided by the denominator of G times the denominator of H plus the numerator of G times the numerator of H, s plus 2. So here's the transfer function. You can also use this feedback command to, and the only difference there is that you have to say that G is equal to transfer function. In this case, the transfer function is 1 plus 2, and then what goes on the bottom is s squared plus 16s plus 60 and 0. All right, so those are quick root loci.